I need to apologize in advance. I came in here yesterday from Europe, so I'm jet lag night for me. So please stop me if I am trying to. If I start saying let's say something completely weird, then this just means that I'm asleep. So please wake me up. Okay, so I will continue the story from the last talk. First I will recall what do we expect from the generic region, and this will motivate the coordinates that I will use to define the Acampo space A. So what should be the Acampo space? I have my model of maximal Calabi-Yaus degeneration, well, the model with properties that were listed in the last talk, and we want to extend it. So this is a holomorphic map with a singular fiber. So here there is a 0, and over 0 there is this fiber D, which is sum of MIDI and SNC thing, and we want to extend it over C log to a C infinity locally trivial vibration. So the Acampo space should be a C infinity manifold with boundary, such that away from which extends the degeneration and replaces the singular SNC fiber by some vibration over the inner circle, and I will refer to whatever happens over this inner circle here as at radius 0. So C log is an annulus, and this circle that's mapped to the center, I will call it radius 0.
So you will actually have the map pi, right? Okay.
Yes. And this will be smooth, and pi restricted to A without the boundary will be an isomorphism from A without the boundary to X without the central fiber. Okay. So then I will construct Lagrangian tori at radius 0, so with the boundary, and spoiler alert, where they will lead. So what will be A? A is this collapsing map pi, so I can define a I circle as the preimage of what Kahler called DI circle, so the corresponding stratum of this FLC. Okay. And so this will be the composition of the boundary. So I non-empty, thank you. And the generic region will be the union of essential maximal of whatever lays above essential maximal strata, and the SM, which stands not for smooth as whatever the Southern I would like, but for submaximal, it is I maximal or submaximal. So we will construct Lagrangian tori here, and they will have good properties here and even better here. And then, because we don't want to construct Lagrangian tori in some abstract space that we invented, but we want Lagrangian tori in actual X. So we will move them along a symplectic connection. And the indefinite article here is because this symplectic connection will depend on the parameter Q from the last talk, so I will be more precise later. Okay, so, and I did not say what, I did not finish the spoiler. So what would be the Lagrangian tori? Well,
sorry, so maximum is bigger than or equal to manifold?
Thanks, yeah, of course. So the what will be the structure of the campus space? Each piece, there will be an intermediate map here to the Kato Nakayama. So the intermediate step of the construction of the campus space will be the Kato Nakayama. And each piece will be, let's call it, let's not call it, will be the corresponding piece of the Kato Nakayama. So it will be, I should write it d I0 log. And because Kato Nakayama is glued in a very weird way, I will, and I need, and this will be multiplied by the corresponding phase of the dual complex. Okay, this will be the structure, and from this you see that there is a map to di0 without log times delta I, whose fibers are tori. And if this is a point, so my phase is maximal, the tori has torus has maximal dimension. And this will be the Lagrangian torus vibration that we will look at. So the tori come from the Kato Nakayama construction. And of course, Kato Nakayama itself does not have any symplectic structure or anything, so we will impose this symplectic structure. But I digressed too much. What do we expect in generic region? So recall from the last talk that we have the fiberwise holomorphic volume form omega, and if I take omega with omega bar and we scale it, so there was some sign, and there was p to the n, we call it vol. I will write omega here to indicate that this is the volume form coming from the holomorphic structure. And I would like to write now the local formula for this volume omega mu. And I will change coordinates, and the coordinate that you will see will be the coordinate in the campus space. So I want to give you first a taste of how the campus space will look like. So I will introduce some definitions on the go. So our map is F, the special fiber is SMC. So locally, F can be written as product of Zi from I equal 1 to some k to the power mi. And this coordinate, some coordinate charge Z1, Zn plus 1, I will call it adapted. So this is adapted chart. And in the adapted chart, I thought so. We told you that the omega should, so omega was theta divided by d log f, and theta restricted to this chart. Well, it is some non-vanishing holomorphic function times it should have a 0 of multiplicity mu I minus 1. That was the definition for the last talk. And then I write dz1 wedge dzk, and I will and the remaining coordinates I just pack in the form zeta, which I will not touch. So this is just notation. So this is this is big theta, so big omega in this charge will be, before big omega, I want to change this formula a bit. So I'm doing this computation because it will be instructive later. So it is C, and now I will write, this is from I from 1 up to K, Zi to the power mu I, and instead of, I added 1, so I need to divide everything by Zi, so I write d log Z1 plus d log Zk and zeta. So once I write this thing and observe that log f is sum of mi log zi very locally, I can write omega as c times, there should be some 1 over m1 product zi mu I d log z2 wedge d log zk. Okay, I'm doing elementary computation, but what is important comes right now. So let me write what is log zi. It is log ri plus, and you will help me, but I will write I in it with a different meaning. So j, okay, theta j, and I will, this will be, I will introduce notation -1 divided by t m j wj plus I theta j, where wj is the logarithmic slope of rj. So it is I will write t divided by tj, where tj is -1 divided by log mi log rj. Okay, this is notation. Unfortunately, I will need this notation. But what does this thing mean? Well, it measures how fast it measures the slope of the variable compared to the it measures the speed of j variable compared to the speed of exponential speed. Okay. So now, and notice that here I write theta as the angular coordinate. I write it additively. Okay, so now I can continue here. So this will be star, and when I make this substitution, what I get is that this is, well, maybe some other constant times the product of Cj mu j, and now I have, when I substitute everything here and pull out t from everywhere, I get t to the power, there is k -1 things, and then I will have a wedge of dwj minus t mj d theta j. Okay, so this is from j equal to, okay, so this is omega locally, and now when I write this volume mu omega, I need to wedge this with its conjugate and multiply by t to the power n. So what I will get, it will be yet another constant, call it c hat, times or maybe I need more space. Sorry about that. The technical part will be over soon. And I will summarize and I will tell you what to remember and what to forget. So vol mu omega is some constant times product of zj to mu j times t to the power. I need to multiply this thing by n, by t to the power n minus k. This is from j equal 1 to k. Times wedge dwj wedge mj d theta j, and I forgot about those remaining things, but they don't matter. So wedge zeta bar. Now look what happened. This thing. Imagine that the wj's and the theta j's are genuine functions, so that there are no poles there. Then this thing will vanish everywhere except for the locus where n plus 1 equals k, so this disappears, and all those exponents are 0, so this disappears. Okay? So let me write so a campus space, write it in words. A campus space will see wj's and theta j's, sorry about, as smooth functions. Sorry, I formulated in a weird way. I just means that wj's and theta j's will be smooth functions on the campus space, which I will define. And then vol omega mu will be a smooth form on the whole campus space, such that vol omega mu restricted to the boundary will be supported where only, so at the boundary t will vanish, right? So I need this exponent to be 0, and I need all those to be 0, which means that I'm on a maximal essential phase. So supported on the generic region. Okay, so I need to define the space in such a way that those guys become smooth functions. Okay, and this is the crucial formula for me. So so what happened now? I made some elementary computation pretending that everything, that there are no poles. I mean, I made a computation away from the singular fibers. And then I say, okay, I will define a space such that those are genuine functions. And then whatever if you say something happens asymptotically, this will really happen in the boundary of the campus space. And this would mean that all the volume of the campus space is concentrated in the generic region. So this already will prove the one of these statements that Javier stated, that the volume of the generic region approaches the full volume of the file. Okay. Moreover, let me comment a bit on this thing. So let's call this star and star. In the generic region, all the multiplicities will be 1. So this thing will actually be, this looks like this, symplectic form to the power n. Okay?
Why wasn't it one at the very beginning? That I missed it. Your simple normal crossing. Why you had the stems as exponents for the seeds in the very beginning?
Well, we did not assume that the simple normal crossing was reduced. So it had we only assume that it's reduced even so that the generic essential components, sorry, so are so now I'm forgetting about this J, but
these ZJs are a choice, right?
what are the
ZJs?
Yes, this is a local expression in a local chart.
Do you say how it changes if you change?
I will say. Okay. I mean, this is just to convince you that I need this and this as functions. And
would the campus be having then a seed function for
yes.
all, not depending on which one?
Well, of course, they are only defined in the chart. So these are local.
All right.
So but there exists global Calabi-Yaus.
There will be global versions of those functions, but not now. Now I'm making a local computation. And because this was maybe a bad choice, but I decided first to make local computation to give you the intuition about how those will behave, and then I will throw at you the coordinates. Yeah.
Just to make sure I understand, so you define your omega to be like that. So you've chosen local coordinates, you define the omega to be like that.
Well, I chose no. The big omega was defined on the previous lecture. So we had this. We wrote something like that: the canonical plus the reduced linearly equivalent to mu I di. We chose mu I. We wrote this linear equivalent, and we chose theta as a section of the canonical. Theta was a global thing, such that theta had zeros of order mu I minus 1. So it was written like this. So that theta has a 0 of order mu I minus 1. So locally, theta must be written as a non-vanishing holomorphic function times the product of zi mu I minus 1, dz1, equal to dz n plus 1, okay? So theta is chosen, and this is a local expression. There is a non-vanishing holomorphic function here, depending on coordinates.
That you still have the C in front.
And this is C,
okay.
And it has a check because I multiplied it by some constant.
Okay, so there is this sort of non-vanishing holomorphic.
Yes. But if I am at in the generic region, so over a maximal phase, this is constant because I'm at a point, right? So once I define my function a, my Acampo space a together with the map pi to x, then here I have a point d I circle where I is the maximal intersection, and over this point I will have a piece of the generic region. And of course, since this is a point and this is the function on x, then this is constant.
So the function on A would pull back from the function on x.
Yes, this function would pull back from the function of x, which is crucial because now you see that when it's on the boundary of the Acampo space, this will not vanish precisely in this generic region when this is constant. So this is constant, times the some 2 form to the power n. So this is how our symplectic form should look like to get this asymptotic Ricci flat. So this would be our dream.
Is the map from the Acampo to the Lagrangian, is that a homomorphic?
Yes.
Ah. So the Acampo gives a different.
No. Well, yes, but not canonical. No, sorry, no. Kahler-Hayama is not a homomorphism. Sorry, I'm like, you need to expand something. You remember that we.
Let's expand the sentence.
Yes, so the piece of the Acampo should be the piece of Kahler-Hayama times the simplex. The Kahler-Hayama is stratified.
And you basically use these expanded pieces to interpolate the tension direction.
Exactly. So you phrased my talk much better than I would. So okay, so good.
But they are homeomorphic, it's just not a homeomorphic.
Yes, they are homeomorphic, but the map that I wrote is not a homeomorphic because it collapsed something. Okay, and also if you look at the omega itself in the generic region, then you already see what was going to happen. So this will be the symplectic form, the Lagrangian tori should be parametrized by theta I. So the tangent space of the Lagrangian tori should be spanned by the vector field which are dual to these d theta j's. So when you restrict the omega to such a tangent space, these guys will vanish, and you will get essentially the wedge of d theta j, so the volume form on the Lagrangian torus, and this will be the reason for asymptotic speciality, because this will be constant. This will disappear since we are in a generic region. This will disappear since we restrict to the Lagrangians, and you will just get the volume form. Okay. So the ideal local picture should look so now, so this was like part 1 of my talk. Now I'm going to part 2, so I will introduce the Acampo space, and so let me draw the local picture. So we would like coordinates. So let's say above adapted chart z1 zn plus 1, where f is product of zi to mi. We would like coordinates. We would like to replace each zi from here by wi, so w1, wk, theta 1, theta k, and the rest I leave zk plus 1 zn, and form some dwi wedge d theta I. Okay, so this is how we would like our Acampo space to look like. And now, if somebody read our paper, knows that this will not work. But let me explain to you why. Sometimes it's better to learn from mistakes. So I will draw what we So okay, so this will not work because I don't include that one. So sorry about. No. We would like to let me draw R1. Let me draw function Z1 times Z2. It has coordinates R1, R2, and we want to interpolate. We want to include those tropical coordinates Wi, W. So we want our Acampo space to look like this. Here, this is the okay, so I draw it like this. So this will be D2, D1, and this D2, 0, D1, 0, D1 to 0. So this would be A1, 0, A2, 0, and the new part is A1 to 0. This is what we want to glue on top of the Nakayama. So these are coordinates of Nakayama, and these are the new coordinates of the Acampo space. This is what we want. And we would like this form. We would like to modify our metric by adding this form. Okay, but what's the problem with this form? Well, this form was designed to mimic Ricci flat metric. And we did something very naive. We just glued a flat metric. Okay, this looks flat, and you see that this is flat. And if you try to prove that it's non-degenerate here at the boundary, so you would like to see, for example, how the monodromy works. You will see that, well, it is non-degenerate in the simplex, but it will degenerate in the corners. Whenever we want to glue this flat thing to these two flat things. Okay, I mean, I can make a computation and show you that this does not work, but it's apparent from the picture. So instead of flat coordinates Wj, which parameterize the simplex, we use coordinates, we call them Vj, and they are defined as Tj. So recall that Tj was just a parameterization of the natural coordinates minus, and if you see what I'm doing, this is T1 minus W1, this is T2 minus W2, but instead of W2, I want eta of Wj, where eta, I will not give you the precise formula, but eta is a very steep function. So when I draw, so let me draw it in the picture. So when I draw, instead of those coordinates, the coordinates V1, V2, the Acampo space starts looking like this. And this is the effect of composing W's with this very steep reparameterization, that now this thing is glued in a smooth way to the U.
Very steep, you mean it's like infinite to orders?
Yes. Eta, so eta is minus 1 divided by 1 minus log eta of s. It's a function whose all derivatives goes to infinity. So now the space will glue smoothly, and if you write the form dvi, where d theta I instead of this stupid thing, then you will also see that the monodromy continue smoothly from here to here. So if you try to compute monodromy with respect to this form, you will get a jump. But if you do this rescaling, you will continue smoothly from here. And also note that because we, instead of Wj, we compose with Wj with such eta, if we impose Vj to be smooth, then Wj will be, well, a smooth function composed with something with the inverse of eta, so it will be very, very flat, very, all the derivatives of Wj will vanish, so Wj will be even more smooth. Okay, so we have two. I gave you local formulas for two forms. A flat one, which is supposed to mimic the Ricci flat one, and the one that has chance to be non-degenerate, at least at the bound. So if you remember Javier's talk, and he told you that there will be a family of forms parameterized by Q, you already know what I'm going to define. Let's call this omega flat. I will write local because it's not like, this is not even my final form, right? This is still local picture. The omega Q, and let's write this local, would be Q times omega sharp local plus 1 minus Q omega flat. This is so this is how the form in the Acampo space will look. So the Acampo space looks like this, and the form looks like, the family of forms looks like this. So this should be how it should work. And now I will give you now it's time for actual precise definitions. Or maybe are there some questions?
I have a question which might be good to pose at this time.
Mm-hmm.
So these Kahler metrics, they are asymptotically Ricci flat.
Mm-hmm.
Do you know if they're asymptotically flat even?
Yes, in the generic region, yes, they will be. Yes, at least this thing. Now I will give you, because this is a local picture. Of course, you cannot expect this globally, so I will show you what happens globally. But I will show you what happens globally, and then we will see. Okay, so this was essentially intuition, and so let's summarize what we have. We define we had coordinates zi, and we define ri, the absolute value, theta I, the angular coordinate, ti, the reparametrization, wi, the logarithmic slope, and vi, the hybrid coordinate. Now, globalize. So, how should we globalize the the radial coordinate? Well, I choose distance functions. Distance function Ri hat from the whole x to positive real numbers, which should measure distance from di. And I require from this distance function, what do I mean by distance function? I mean that in the adapted chart, so in every adapted chart when I have Ri hat should be some positive function, depending on the chart times Ri. Is an exercise for you to prove that such distance function exists. If you want, you can look at your DI, cover it by charts, and glue the local functions by a partition of unity. Once I have this distance function, I can repeat the definition by putting a hat here, putting a hat here, and putting a hat here. And now comes the crucial computation. That if you take this function wi hat and I need to write it like this, that as f approaches 0, wi hat does not depend on anything, on the choice.
So it's even better to say wi hat equals
Yeah.
wi plus dA. Because t goes to 0.
Yes,
Very
so
precise, very precise.
let me prove it, and then so what is wi hat? Well, if I use the definition, so if I substitute everything, this should be log modulus of f, and here I would have my mi log ri hat, and when I substitute this, you will see that this is mi log lambda divided by log modulus of f plus mi log ri divided by modulus of f, which is wi. Okay, and now when modulus of f goes to 0, this thing goes to 0. And even so, this is t times some positive function.
But it's important that it's t for fiberwise computations.
Yes, but I will not do those fiberwise computations because I don't have time. Okay, so when we leave the local picture, and now so now maybe it's time to define the campus space as a space, because I still didn't do it, and it's really high time. So what is the campus space? I start with F to C. I extend this to Kato-Nakayama. So this is the Kato-Nakayama space. And if you don't like Kato-Nakayama, you just locally extend the angular coordinates, because that's really what it is. You do a real oriented lower velocity component and trust that this glues well to a topological space. So I extended the angular coordinates. So now I extend the radial. So I need to extend the wi hat. So I have a map w1 hat, w big N hat, where big N is the number of components, to Rn. This is a partially defined map, so in order to make it a true map, I call it mu and take the closure of its graph. This is some horrible topological space, and now I take a fiber product. And this is the campus space, the topological space. And note that there is a philosophical principle in this diagram that we treat the angular and the radial coordinates separately. And that's the underlying principle also of the definition of the forms. So let me say the theorem, which is almost true, but
I just want to say something else. So when you approach to radius 0, when you approach to the central fiber, this W1 hat, Wn hat approach precisely the dual polyhedron.
yes, the thing that we glued here, the red thing,
It's really the
is
dual
parameterized by Wi, well, the local guys, but the local guys at radius 0 equal the global guys, so it doesn't matter. And this W, this is precisely the coordinates of the dual polyhedron at the boundary, so at the figure that we glued.
So the campus space is like a hybrid space that combines the blue geometry of X, the angular coordinates, which is the kata Nakayama, and the dual polyhedron. So you chop everything conveniently, make products, glue back, and you have a campus space.
So the campus space has charts, and the charts, well, I will cheat you a little bit, but just a little bit. So I cannot take these charts, but I take the chart with vi hat, theta 1, theta k, and zk plus 1, zn, and though A with a C infinity structure, such that the functions that you see here, the vi hat, the wi hat are smooth. And the map phi here is smooth. So,
And A is a locally trivial vibration over
yeah,
C log.
so and
this
this
where you
is a locally trivial vibration over C log.
So the point is that if you want this to be a locally trivial vibration, the charts are slightly different. I wanted to say where you cheat.
Yeah. I treated it because if you do something like this, then this I should replace locally each one of those so one of the coordinates behaves almost like the radial coordinate of C log, so I need to exchange this for the radial coordinate of C log suitably parameters. But I didn't want to give you one formula more. But that's the idea. So the idea is that we force the vi hat to be smooth, and this automatically, well, automatically after you do 50 pages of computation, but automatically forces the wi hat to be smooth, and this is the smooth manifold. So now I can define the forms, but I didn't tell you how to globalize the angular coordinates, and I won't tell you because it does not make sense. How can you rotate about 30 degrees of a divisor that's in the other room? It doesn't make sense, but the angular form makes sense. So
You
note
cannot
that
globalize because there is a Chern cluster construction.
that's the mathematical way to say it. So recall that d theta I is minus dc log ri. So I can define alpha I hat, which is no longer an exact form, as that's the Chern class abstraction. Alpha I hat as minus dc log ri hat. And now I can define the omega flat and omega sharp as maybe I will define the exact forms as sum of wi hat alpha I, and this is sum of vi hat alpha I hat, and this guy at radius 0 behaves almost like this guy. while this guy, well, d of, so omega flat will be d lambda flat, and omega sharp will be d lambda sharp. And this guy is like this is like this. So what is easy to see is that omega flat is ddc of a potential. The potential is, as you might expect. And what is slightly more difficult to see, but also true, is that this is also a ddc of some potential. So phi sharp is some function x minus b to r, and I don't write the explicitly because I need to compute an integral. It's not elementary, but modulo computing an integral, this is also explicit. These equations are fiberwise over.
What's written as a denominator there for omega flat?
Omega flat, this is
minus 1 over,
over 2t.
2t.
So this is some rescaling, and this is just what you would expect from this form, right? It's a sum of, it's a Euclidean distance, only in the hat coordinates. Okay, so
What's it? D theta I equals minus dc of log of what? Just
so
Log of Ri.
yes, this is the definition of the angular form. This is Ri. This is how the angular form works. It's minus dc of log Ri. Because theta I, well, this is, and I want to mimic this, so I make the same definition, but with the hat function. And the difference is that, well, this is a local form, it's closed, it's exact, and this is not exact because it's not.
because you can vary Ri, kind of continuously, but you cannot vary theta.
Exactly, yeah. So the cohomology, so the I will say something stupid, but alpha I hat is related with the first-term class of the normal bundle of di. So what's the first-term class? It's the obstruction of having a section. So if I had a global angular form, I would have a section of the norm circle bundle in the normal bundle. But of course, this normal bundle can be non-trivial, so I cannot have a section. And that's why the alpha I hat is not even closed. It's not closed. It's a 1/4.
I lost a little track. So what happened to the Fubini-Studi form?
Well, it is going to appear on the blackboard now. Yeah?
Is it obvious that A doesn't become an actual complex structure?
It does not. It is not obvious because it's not true. A,
How is DC?
this DDC is this is a lie. It is fiberwise over C star. This makes sense only away from the central fiber.
The theorem, so you define away from the central fiber, but you find an expression in terms of Wi hat. And in the previous theorem, you proved that the Wi hat are smooth in the Acampo space. So whatever you define using the complex structure inside extends smoothly to the Acampo space.
So this is the maybe this is the definition. This is the smooth form in the Acampo space, and this is a formula that is valid only at positive radius. So these forms are of type 1,1. So the omega flat and omega sharp are of type 1,1 wherever it makes sense at positive radius. So I will write the theorem. So I define omega q epsilon as pi upper star of omega x plus epsilon. And now this linear combination, omega sharp plus 1 minus q omega flat. And the theorem is that there exists an epsilon 0 and a delta such that first, for all q and all epsilon, the form omega q epsilon is fiberwise Kahler over d delta star. So this is the disk of radius delta. And so recall that my vibration is over c log, but I shrink the radius to d delta log, and I identify the interior with d delta star. So this is just saying what happens away from the new part. That provided my epsilon is not too big, I did not destroy positivity at positive radius. Part B says that for all q positive and for all epsilon positive, omega q epsilon is fiberwise symplectic over d delta log. So this is the additional thing that in the new part, they are still fiberwise symplectic. And there is also part C that for all epsilon positive and for all maximal essential, for all actually essential, doesn't matter if it's maximal, there exists a V epsilon. It is a neighborhood of the interior in the boundary of the Acampo space of the corresponding piece of the Acampo space, such that omega epsilon, omega 0 epsilon restricted to V epsilon is fiberwise symplectic over, well, fiberwise symplectic simply. So the point is that I already told you that if I just take q equals 0, so I just take the flat thing, it cannot be non-degenerate at the corners, but still here in some neighborhood it will be non-degenerate, which will be important for any computation concerning degenerate regions, where we really want to pass with q to 0. So, because I see I'm running out of time. So what does this computation, well, what does this theorem tell, and where is the difficulty? The difficulty is actually here, to say that when I add this strange stuff, which certainly dominates when I go to radius 0, because, well, I glued some new parts, so omega x becomes degenerate there, that I don't destroy positivity. Once we prove this, so we prove positivity, then this is essentially a computation at radius 0. You need to compute that the form is not degenerate, so we need to compute the monodromy vector field that is unique, and this is easy.
Yeah, in principle. So in maximal phases, what you say, there is a radius 0 part in which there is a combination of arguments. But what you said is.
What I want to say that is important here, that epsilon is positive, because of course I cannot do it with just omega x, and that q is positive, because I cannot do it with the flat form alone. I need this Acampo form, and nobody corrected me here. It's also important that I take all the divisors, because I need to fix whatever, sorry, not here, the sharp thing takes care of non-degeneracy. So I did all the divisors in the formula, but the flat thing is designed so it sees only the essential. So the sum is taken over the essential phases. Because I want to see when I go with Q to 0, I want to see only the essential phases and not all phases. So I define it so that it does. So that it does the job. And now I can just repeat what are the Lagrangians. Well, the Lagrangians at radius 0 are easy. So now I recall the picture of the Ocampo space in 2 dimensions. It looks like this. This is A1, this is A2, this is A1, 2. And AI has the structure of the corresponding piece of Kato Nakayama times the simplex. And the projection to DI0 times delta I. Well, the fibers are tori whose tangent space is spanned by partials with respect to theta I. So if you substitute to these formulas, you will see that they are isotropic. So these fibers are isotropic tori. So in particular, the generic locus of the boundary is fibered by Lagrangian tori. And what about submaximal? So if I is submaximal, then AI is DI, well, the same thing, to DI circle times delta I. But now this is an open Riemann surface. And Javier told you what kind of open Riemann surface it is. It is a C star, because we chose our model. So that this thing is, well, P1 with 2 points removed. So it has a natural vibration by circles. And when I compose with this vibration, I get here R times delta I. And this is also Lagrangian by a very stupid argument. Recall that the form is like sum of D, whatever, dW, dV, wedge, d theta I, or W's. And the tangent space to the fiber is spanned by partial with respect to theta I, and precisely one vector, which is tangent to the fiber of this height function H. But there is only one guy, and whenever I fit this, I vanish, and the form has 2 slots. So on one slot, I will plug this thing, and this tells you why this will not generalize to higher codimension, because in higher codimension I have 2 vectors which are not of this good form. And once I have Lagrangians at radius 0, I just pull them to positive radius by symplectic connection. So recall this our biparametric approach. I approach both with parameter q and the radius to 0. So at each point I have the fiber with z of h with omega epsilon q of h. And to produce Lagrangians, I start with from here and use the form omega q for positive q to pull Lagrangians from radius 0 to my fiber, using the form omega q because q is positive, so I'm allowed to do it. And the computation that I showed you in the beginning proves now in a very precise way, because wi, theta, I are genuine functions. So the computation that was asymptotic, whatever, now is really valid. So if you recall this computation, the computation makes sense in the campus space. And it proves that the generic region has full volume, that the Lagrangians are asymptotically special, that the form is, that the basic is asymptotically region flat, and all the properties that Javier told you at the end of his lecture can be proved by a direct computation at radius 0. So, like, I know that there was a lot of technical details, but the summary, the philosophy that I want to sell you is that the Acampo space provides coordinates where the asymptotic computation can be phrased as an actual computation in some smooth coordinates using smooth forms. And they are canonical, independent of the choices by the kind of crucial computation that was in this piece of the board, where I compared the wi hat with wi. And I'm sorry for going over time. I will stop here.
Yeah, thank you.